Hi there. Thank you for clicking on this video. In this lesson, we're going to talk about solving logarithmic equations, or we'll often just say log equations. Please give this video a like if you find it helpful. Only takes a second to do that. Drop a comment or a question to engage. Subscribe to the channel for more math help, and please check out the practice set for this lesson. It will be linked at the end of the video. I wanted to start off with this umbrella overview. What is a log equation and how do we solve it? Well, shortest way to define this, any equation that involves a log, it could be a regular logarithm or a natural logarithm that involves a log, would be a logarithmic equation. And while there's always exceptions to rules, and if you dug around hard enough or hunted around, you could always find something that is a little bit different. Basically, there are two main strategies that we use to solve logarithmic equations. The first is to set the arguments equal to each other, and that looks something like this. If you had the log of x is equal to the log of 2, that you would be justified in saying that x must be equal to 2, because you wouldn't say that the log of 5 equals the log of 2. That would be an illogical statement, that the only thing equal to the log of 2 would be another log of 2. Now, there are some ways that it's okay to picture this and other ways that I would strongly caution against, and we'll kind of get into that when I go through an example problem. The other main strategy is to take the log and change it into an exponential. And if you've followed along with this series of videos on this channel, you know that when we were solving exponential equations with logarithms, I kind of took you through a process of taking the log of both sides, but then showed you this shortcut sort of where we developed this statement here, which is if you have a base raised to an exponent and that is equal to some number, that can be changed into the logarithm of a base of with a base of a number is equal to the exponent. Well, when you're solving a log equation, you would go in the other direction. So you might have the log of something is equal to an exponent, and you would do that little number and change it back to an exponent. And it's a little bit easier to see the process going the other direction, where you're taking the log of both sides and then using the inverse nature of these operations. This is a little bit trickier to see, but you're essentially doing the same thing, just in the reverse direction. And the easier way for us to picture it is just changing the form over. So if you need to, please go back in this playlist and check out some of the earlier videos where I introduce what is a logarithm and how to solve exponential equations with logs. And if I can remember, I'll try to link those in the description box so you can find those videos there as well. Now, solving log equations may also involve using the properties of logs. Okay, so we might need to rewrite a logarithmic expression so that it fits a form where these strategies would work. It often will involve solving quadratic equations. So everything we know about quadratics, using the quadratic formula, factoring, all of that can come into play. And something that this is one of the first main places where it shows up, but checking for extraneous solutions. And these are solutions that come from the algebra, but do not actually make the equation true. And so with some equations, we don't need to check for extraneous solutions. We can just trust that, hey, if the algebra gave us the solution, it'll work, provided you did the algebra correctly. But what we're talking about here is a situation where you can do all of the algebra correctly and still get a number out that does not check. So why do we need to check the solutions? There are many different ways I could try to explain this. I kind of settled on this one way, but again, if you feel like I'm leaving you with some questions here that are unanswered, please drop a comment, ask that question so that I can refine my explanation or address the question that you have. So this graph shows y equals log base 2 of x in purple. So we've got this function right there. That's y equals log base 2 of x. So that's our logarithm. You can think of this as being like the equation we want to solve because we're talking about log equations here. Note that the purple function has a restriction on the domain, namely x has to be greater than 0. So this right here has this vertical asymptote at x is equal to 0, and the function only exists when x is positive, where the exponential does not, okay? And so the exponential here is the one in red, and this one is y equals 2 to the x. So if you were to take the logarithm and change it to the exponential, okay, remember that's one of our strategies that we can use. Take a logarithm, change it to an exponential. We are going from something that has a restriction on its domain to something that does not have a restriction on its domain, because this red function will exist everywhere. So sometimes we'll get an answer that works for the exponential, but will not check when we test it back in the original log equation. This often happens when we see quadratics. The quadratic will generate two solutions, and many times, though not all the time, one of them will not check. And sometimes I'll have students ask me, oh, well, when we get two solutions, one of them checks and one of them doesn't. Well, no, not necessarily. You can get two solutions that both check, but you do have to like go back and check and see if they work. Now, a key thing that we're going to be looking for is when you're taking the logarithm, remember that the argument of the log, that's the thing that you're taking the log of, must be greater than 0. So a lot of times when we talk about checking to see whether or not a potential solution works, what we're actually looking for is when I plug that number back in, will I be taking the log of a positive number, or is it going to show me that I'm taking the log of a negative number? So that is typically what we're going to be looking for when we're doing these checks. So that is one way of kind of showing with a graph and explaining why it is that we can end up with these extraneous solutions and what it is we're going to be looking for when we do that check. So here's an example of setting the arguments equal. So we have log base 5 of 3x minus 1 equals log base 5 of 2x plus 7. And the quickest way to do this is to essentially see, okay, I have the log base 5 is the same on both sides. And if these are truly equal, then it must be true that 3x minus 1 is equal to 2x plus 7. Then we would subtract the 2x from both sides. So we get x minus 1 equals 7. Add 1 to both sides, and we get x is equal to 8, and we just get that one solution. Here's what the check looks like. You can do this in your head even, because again, we don't really care what the number is. What we care about is whether the number is going to be positive. So we would check 3 times 8 minus 1. Well, that's 24 minus 1. That is positive. And 2 times actually any positive, that's all positive. So this does check. We just, again, want to take those answers, plug them back in, and make sure that every logarithm in the original equation will end up being the log of some kind of positive number. Now, before we move on from this, I do want to be clear about what is and is not happening here. So I usually tell my students, I am okay with you thinking, oh, the log base 5s cancel out, okay? Because they kind of do. So what we're going to do is we're going to unlog both sides. Whatever that process is, we're going to unlog both sides. In fact, this is what we're doing here. Is we're doing 5, we're like raising each side with a base of 5. So if those two log expressions are equivalent, then I could use them as exponents. And then if you've watched earlier videos in this lesson sequence, you know that the base of 5 and the log base 5 end up canceling each other out, leaving you with the argument. Now, this would be really rare that you would see somebody do this because it is a lot of writing to get you to a much simpler place, and the intuitiveness of this step, usually people don't have a problem with it. What you cannot do, okay, and I want to be really clear about this because in our heads, sometimes we say cancel out. That technically, I'm okay with that. Now, your teacher might not be okay with that. So that's where you want to be careful when you're getting a video off the internet, that the way I explain something or what I am okay with my students doing or showing might not exactly match what your teacher is okay with you doing and saying. But the next thing, this is wrong. You cannot do this. Okay. So put your pencil down if you're taking notes. You may not do this. Okay, and then show the canceling that way. And I want to be really clear about that. That is division, and division undoes multiplication. But this is not log base 5 times anything. One of the teachers at the school where I work tells their students you cannot have a naked logarithm. And by that, what the teacher means is you can't have a logarithm without an argument. That is completely wrong. Okay, if you were taking an advanced placement exam where you were graded on some of your work in the FRQs and so forth, this would be very costly because that is not what's happening. So can you think of it as we're going to unlog both sides? Yeah. Are we going to cancel the logs out? Do the two matching logs cancel each other out? We could just undo them? Absolutely. Could you do 5 to the and then make each side of that equation an exponent? Yes, you can do that too. Can you divide by logs? No, 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 no. Okay, you just cannot divide by a log base 5. So again, I know I've hung out on this slide for a long time for such a short problem, but that is a big conceptual thing that we want to make sure that we are getting. All right, so this is the other strategy, and there's a couple ways you can do this. I'm actually going to show you a few ways to do it. So one of the ways that I've had my students do this is we have like off to the side this little statement, log base b of n equals x, and that's our statement for converting from an exponent to a log and back and forth. And then we remember that the natural log is log base e, and that is intended simply to change the form of the notation so that these two match. So the way you've got this written matches the way it's written over here, so that you can clearly see what the b is. And now we're going to change the form over. So we're going to have b to the x equals n, e to the third equals 4x plus 9. Now the other way, so alternate way that you could do this is do what I did on the previous slide, and that's take each side, not raise each side, but like take each side and raise it with a base of e, and then recognize that the e and the natural log cancel each other out, leaving you with 4x plus 9 equals e to the third. And you can see that that got us to the same place. Whichever way your teacher would like you to do it, and whichever one of those ways makes the best sense to you, not just replicating steps, but seeing what's happening in the solution of the problem. So now we've got a couple of options. I'm going to show you what it is to get the exact answer. So mathematicians often do not like to round, and so we're going to solve for x, and we're going to keep the e to the third as is. We're going to go ahead and subtract 9 from both sides. So e to the third minus 9 equals 4x. And then divide both sides by 4, getting e to the third minus 9 over 4 is equal to x. And that is an exact solution. So there's no rounding going on in there at all. Scientists and engineers would not probably find that very useful. And so scientists and engineers are going to want to evaluate that. And so I am going to, on my calculator right here, e to the third minus 9, all divided by 4. And I get 2.7713842331. We'll round that 2.77. We'll do 14. And that is what we would call an approximate solution because I have rounded that off. Okay, and so again, follow directions that you are given in your class for whether you are asked for an exact or an approximate. And if you are asked for an approximate, that you know how many decimal places. Usually it's 3 or 4. Once in a while, you might just need to do 2 decimal places, but I would say usually it's 3 or 4 decimal places out, and that you are correctly rounding and so forth. So also knowing how to use your calculator to do it. So every calculator is a little bit different in how you would go about doing that. I had to finagle some parentheses with what I did just now. Oh, and we should check this out. So again, we want to make sure before I move on, I don't want to get lazy about the check. So here's what I'm going to do. I need to make sure that I'm not taking the logarithm of a negative. Now, what I notice about this is that that is a positive number. Okay, I don't want to tangle with that number. If I do 4 times a positive number and add 9, I am getting a positive number, and so I know it will check. So again, that check does not need to be like, you don't have to grind it out with messy decimals and such. Like what you're mainly looking for is the argument of the logarithm going to be positive. So positive number, 4 times a positive plus 9, it's positive. Actually don't care what the number is. All right, here are a couple of additional examples, so we'll just go through these. This is one that does involve needing to use the properties of logs. And so what I've got there is I have 2 logs being added together, and if you don't remember the properties, if you have 2 logs being added together, those could be written as a single logarithm, and you would multiply the arguments. So this is going to be log base 3, and we're going to multiply the x plus 5 times the x minus 3. And now I'm going to change that over. So this is 1 logarithm. I'm going to go ahead and change it over. So I'm going to have 3 to the 2nd power. And I need to multiply this. So I'll do the work out. Okay, and so that's 9, and this will be x squared plus 2x minus 15. That is a quadratic, so we're going to set it equal to 0. X squared plus 2x minus 24. This is factorable. So this will factor into x plus 6 times x minus 4. And so we have x plus 6 equals 0 and x minus 4 equals 0. And this is one of those situations where, yes, we have 2 possible solutions. So I could have x is equal to -6. That will make the quadratic true. And x equals 4, which will also make the quadratic. But remember that, like in solving a quadratic has no restrictions on its domain, but the logarithm does. So taking a quick look at checking these solutions. So again, we don't need to like overdo it with the check. -6 plus 5 is negative. That does not check. 4 plus 5 is positive, and 4 minus 3 is positive. So the 4 does check. And that's really all the check needs to be. As always, follow your teacher's directions on like what to show for a check, what is gonna be acceptable, okay? But to know that the -6 does not work, but the 4 does. You plug a -6 back into the original equation, your calculator is gonna error on you because you're plugging something in that's gonna be off of that graph. Not going to work. But there we go. Now there's a lot involved here, and I went through it very quickly. I've been on this problem less than 3 minutes, and I know for my students, this is probably going to take a lot longer than 3 minutes. I quickly solved that quadratic, quickly factored it. I did not go through all the steps of like multiplying the x plus 5 times the x minus 3. I've done that a million times. I can do it without showing any work. And the same with the factoring into the x plus 6, x minus 4. If you need refreshers on that, we do have a bunch of videos on the channel. Go check out the quadratics playlist. And I go through a lot with how to do the factors, and make sure that if you are in class and you are like, I'm getting the logarithm part, but I'm messing up the quadratic part, that can be a valuable way to ask a question to your teacher. So the teacher knows, hey, like I'm understanding what to do with the logarithms. What I am weak on is solving the quadratics and factoring, and then follow your teacher's directions from there. Great, and here is another example. We have natural logs here, and so here we are subtracting. And so if you recall, if we are subtracting two logarithms, we can write that as a single logarithm where we divide the arguments. So this will be the natural log of x over x minus 5 equals the natural log of 3. And for this one, we are going to simply set the arguments equal. We're going to unlog both sides, or we could think of it as the natural logs cancel each other out. Since we're doing the same thing on both sides, we're just going to undo the same thing on both sides. Do not divide both sides by an ln. That would be wrong. Do not do that. So where does that leave us? That leaves us with x over x minus 5 equals 3. Now, at this point in the development of my channel, I have not done any videos on rational equations. This is a rational equation. It's not a sophisticated one. It's a fairly simple one, but we should be able to go through it. So this is division right here, okay? Right there, that's division. That's supposed to be an arrow. Okay, and so you think to yourself, all right, that's x divided by, how would I undo that division? And the answer, of course, is I would multiply. So I'm going to multiply by x minus 5, and I'm going to come over here and multiply by x minus 5. So if I have x and I divide it by x minus 5, and then I multiply by x minus 5, well, dividing and multiplying are going to undo each other, bringing me back to just x. On this side, we'll go ahead and distribute. So we'll have 3x minus 15. Go ahead and subtract 3x from both sides. You can also, of course, subtract x from both sides and add 15. And then divide both sides by -2. And a negative divided by a negative is going to give me a positive, or you could use the decimal there. And then we again want to make sure, we're going to do a quick check of that. So our check is something like this. Since this is a positive number, the first log checks. Okay, now this one, we're going to take that number and subtract 5. So what we want to be careful about there, 7.5 minus 5, that is positive, and so my answer does check. There we go. All right, and this one I think is messy, and this video is getting very long, like a lot longer than I thought it was going to be. Okay, so for this one, we are going to use this property of logs, which is, I don't even know how I did this, but if you have log base b, log of a log of b, that's log of b to the a. I don't know why I switched my variables up there, my letters, but essentially this is the property that allows you to take a coefficient and move it into the exponent and vice versa. And so this too is going to migrate into becoming the exponent. And now I'm going to set the two arguments equal. And I have a feeling this one that comes out like really not Great. Okay, now I am going to try to expedite this a little bit by saying x plus 1 all squared means x plus 1 times x plus 1. That's what it means to square something. And then squaring this will be x squared plus 2x plus 1. This brings us to a quadratic. So we need to get a 0 on one side. I'm going to do that by subtracting 9x and adding 3. And so that's going to give me x squared minus 7x plus 4 is equal to 0. And that is not factorable. So this is going to run us into the quadratic formula, which is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So we will have the opposite of b, opposite of -7 is 7, plus or minus the square root of -7 squared. Well, -7 times -7 is positive 49, minus 4 times 1 times 4 all over 2a, or 2 times 1. This is 7 plus or minus the square root of 49 minus 16 all over 2. So we have 7 plus or minus the square root of 33 all over 2. And what we need to do there is do a check on this. So I want to make this as painless as possible in terms of doing the check. So what I need to do, and when I was doing this out, this is the work as I would do it. I did not do extra steps because I am watching the time on this video. But yeah, so I did go through that very quickly. I didn't plug in all the things and do all the steps that I could have done. I actually did this the way I would do it if I were sitting with a piece of paper in front of me and somebody said, solve this using the quadratic formula. Okay, so looking at this, looking at 7 plus, so the positive one here, okay? If we look at the positive solution, so 7 plus the square root of 33 over 2, that is a positive number. If I take a positive number and I add 1 to it, I will have a positive number. So we're good with that. If I do 9 times a positive number minus 3, I think most of the time we're going to be dealing with a positive number there. Where it's going to be an issue is if the positive number that I'm multiplying by is significantly less than 1. However, 7 plus something over 2 is not going to be less than 1 because 7 over 2 is 3.5. And so even if I didn't add in the root 33, whatever monstrosity of a number that is, it would still be greater than 1. And so 9 times any number greater than 1 minus 3 is also positive. So the positive does work there. Now we want to look at the negative. So we are good on that one. This is the 7 minus the square root of 33 over 2. And for this, we kind of need to know 7 minus the square root of 33, is that positive or is that negative? Well, here's how I'm doing this. I'm trying to avoid using my calculator here. The square root of 33 is less than 6. How do I know that? Because the square root of 36 is equal to 6. So the square root, since the square root of 36 is equal to 6, the square root of 33 must be a little bit less than 6. And so this number right here, we're going to be doing 7 minus 5 point something. That's going to be a positive number. And so this one, if I take a positive number and add 1 to it, it's still going to be positive. So that leaves me with this one that I need to check, because this number I'm not confident is greater than 1 by a margin that's going to guarantee that that is going to end up being big enough that I can subtract 3 from it. So now finally I have to grab my calculator and I do 1 minus the square root of, square root of 33 and divide that by 2. And I have 0.6277. So that is less than 1. Now it is possible that we could do a number less than 1 and still have it be big enough. And I'm inclined to think this is going to be fine because 9 times a half would be 4.5 and 4.5 minus 3 would still be positive, and this number is greater than 1/2. But we will double check it just to be sure. So I'm going to add, multiply by 9 and then subtract 3. And I get 2.6 something. And so that looks like that is going to check as well. And so both of those end up checking. So yay. It's a mess. And this video has now cracked the 30-minute mark, which is not what I wanted to do. So we'll wrap it up very quickly. Please don't forget to give this video a quick thumbs up, subscribe for more math content, drop a comment, say, hey, you went over 30 minutes on that and I did not sign up for that. But it would have been longer if you had done this lesson in a class, almost for certain. And then please check out the practice set linked below, or go get a snack and a drink of water and then come back and check the practice set below. But make sure you check that out. I'll make sure I link that, and I hope to see you in a future lesson.